All right. Hey, wanted to welcome you to this latest educational offering, help you with breaking down some of the most commonly confusing and conceptually difficult topics in GIS. This one focuses on raster resolution and resampling. That's me, Dr. Michael B. There in front of Woodburn Hall, in the lovely downtown Morgantown campus. Just off to the right out of screen is Brooks Hall. That's where my office is located. I'm in the Department of Geology and Geography. If you want to shoot me an email, if you have questions, you want to ask me something, go right ahead. If you're interested in our programs, check out our website. And if you're interested in an online master's degree, there'll be a little more information about that at the end. All right, raster resolution and resampling. what does Where do students go wrong with this? What really gets their gears grinding? What causes them to have sleepless nights about this topic? Well, it's a couple of points here that we're going to sort of go over. One is confusing resolution with accuracy. Another is not grasping that cell size is actually an area. Uh, Another mistake is thinking that resampling adds more detail, or picking the wrong resampling method, or misunderstanding how projections and resamplings, what that does together, um, losing track of units, and ultimately trying to just conceptualize what actually happens to the numbers when we do these things. So, why students confuse resolution with accuracy? Resolution simply means pixel size. How much ground does one cell cover? That's it. Accuracy, on the other hand, means how close is that pixel's value to the real world truth of that area. And what happens is students often assume that smaller cell size means better data. They assume that higher resolution imagery equals more precise numbers. And they think that resampling to a smaller cell size somehow improves the data. But the truth is, none of these are necessarily true. Accuracy in raster data is really how well that pixel value represents reality, not how big or small the pixels are. Rasters can have a very fine resolution, in other words, really small cells that look detailed, but they could still be wrong. They could still be inaccurate. If the underlying measurements that were collected were wrong, if it was based on some remote sensing and somebody used a wrong calculation, if a sensor was out of alignment, if somebody missed a decimal on a GPS coordinate, any number of things can make it wrong. Accuracy really has two components, positional and meaning. Positional accuracy is the first one we're going to talk about, meaning each pixel is correctly located on the ground. And then there's attribute accuracy, meaning that the values that's stored in the pixel, whether it's an elevation or a temperature or a land cover class, it's really close to what that true value should be for that pixel. Higher resolution does not guarantee high accuracy. It only means smaller pixels. And creating smaller pixels, though, through something like interpolation, doesn't add information. It doesn't improve accuracy. It just redistributes the existing data in a different raster grid space. Precision in raster describes the level of detail or exactness in how values are stored or reported, not how close it is to being the truth. So you can be precise and get repeatable numbers, but that don't mean them right. That don't mean they're right. They can still be wrong numbers. A DEM might record elevation to the nearest centimeter or the nearest meter, but neither one of them tell you whether those numbers are actually correct. That's what accuracy is. Precision can also refer to statistical consistency or repeated measurements, that sort of stuff. In raster, students often mistake high resolution and many decimal places for high precision and high accuracy, but they're really separate ideas. A raster can report values with 6 decimal places and still be wrong by several meters. Um, Part of what causes this, I think, to some extent, is they'll kind of fail to grasp the idea that cell size refers to an area. Many students like to think of raster resolution as a point spacing, like the data points are 30 meters apart, like sample points. But it's not that. It's a grid. It's a 30 meter by 30 meter square, a collection of 30 meter by 30 meter squares, columns and rows. And this leads them to misunderstand what the value really represents in that cell. They picture a single measurement at the center of the cell rather than a value that is applied to the entire area. If you think about it from an elevation standpoint in a DEM, on a 30 meter DEM, one cell represents a 30 meter by 30 meter area, or 900 square meters of ground. If that cell's value is 903, that means that the elevation across that whole 900 square meters is approximately 903 meters. That single number is assumed to represent the entire cell, not just one point in the center. And that's just the wrong way to kind of think about it. When you collect raster data, it's captured at a specific resolution and accuracy, and the level of detail determined by the sensor or measurement process. When you resample it, you're not collecting anything new. You're simply creating a new grid and filling it with the values from the other cells, with values based on that old grid. Whether you make the cells smaller or larger, the underlying accuracy and scale of the information is the exact same as what it was when you collected the prior data set. All that changes is the spacing of the grid, nothing else. Students often realize that the choice of resampling methods depends on the type of raster data that you're dealing with. They might just pick whatever the default is or what looks the smoothest without really thinking about what they're doing and why. And that can cause you to generate some distortions, and in some cases even generate just completely meaningless results. So rather than spend a whole lot of time trying to explain each of these and what they are, I thought I'd just give you the short list. So this is picking the wrong resampling method simplified down to the 4 most common techniques for resampling, and then what kind of data we would use that on. Nearest neighbor for anything that's categorical. Why? Well, nearest neighbor is just going to say, okay, here is my new cell. What's the closest one I got? And it's going to call it the same thing. Bilinear is something we would use for continuous data. Here's an elevation of 10. Here's an elevation of 12. My new point's in between. Add 10 and 12, average them, I get something in the 11 range. Well, that's probably what it's going to be. Cubic convolution, same concept. The only difference between these two really is just the size of the area of influence. One looks at 4 cells, one looks at 8. The majority function looks at the most common value within that space and picks that. So it's similar to nearest neighbor, but instead of just looking at one cell, it looks at a larger area. Again, for categorical data. The reason you don't flip these things around is because, if you're looking at categorical stuff like land cover, how do you average pasture and row crop? You can't. It's got to be pasture or it's got to be row crop. So you have to figure out ways to do that, and that's really what this simple list here is about. It's about telling you that, hey, if I have categorical data and I'm going to resample, it's got to be either nearest neighbor or majority. And then you can work through each of those and figure out which one is the best for what you're doing. If you have a continuous data surface, temperature, elevation, rainfall, then you know that if I'm going to do something with this, I have 2 options, bilinear interpolation or cubic convolution. And I need to examine each of these techniques and see which one is the best for what I want to do. When you project a raster or reproject one, it usually has to be resampled to fit the new grid in the new coordinate system. So unlike other data where we were just, bending and twisting all those vertices, with raster data, we've got a grid, okay? And when we come up with a new coordinate system, we're coming up with a brand new grid that's aligned in a brand new way. And what we have to do then is fill that brand new grid with values from that old grid. And that's a little different approach. What students don't often realize is that projection isn't just a geometric transformation. It literally changes the layout of the pixels, and that may change cell sizes even slightly. And so it's a significant undertaking. They also don't understand that this requires recalculating pixel values or resampling, which can slightly change the data. Where you see this the most is when you have a beautiful image and you have to reproject it into a different coordinate system, and afterwards all the colors are off. Why? Because you shifted it just a little bit. Cell size may change when going from degrees to meters or from one projection to another, not because the data got better or worse, but because the measuring cell width and because you're measuring the cell um, width in a new unit system. Uh, Values can change slightly depending on the resampling method chosen, especially if you're looking at continuous stuff like bilinear and cubic. Students should always check, your new cell size after you reproject. Is it what you wanted? You should check which resampling method was used. Was it the one you wanted to use? And whether it's acceptable for the analysis that you're doing. Did you make the right choice? Losing track of units is something that happens too from time to time. Many rasters store cell sizes in the units of the coordinate system. And so when you're looking at the cell size and you have a very, very, very tiny number, it's because it's probably representing some sort of an angular thing, which means you're in a GCS, which means you should not be doing that analysis you're about to do until you reproject that data. Or is it in meters or is it in feet? That can really make a big difference, because when you start thinking about things like buffers and things like that, are you going to buffer to a certain number of meters or a certain number of feet? You really need to think about this so that you understand what the numbers mean. Um, if you interpret something as a ground distance and it's actually an angular measure, everything that you get from that's going to be wrong. When we reproject the raster, the cell size changes numerically, but students sometimes think that the data resolution changed rather than just the units. So always check the CRS units before interpreting the resolution. In a geographic CRS, resolution is in degrees. Ground distance per degree changes with latitude, so that's just a horrible thing to try to measure with. In a PCS, it's in meters or feet, and it's consistent across your map. Reprojection doesn't improve or degrade the resolution, it just expresses it differently in new units. So always look at what the units your cell size is in before you assume that the data got more or less detailed. And again, never do any spatial analysis in a GCS. Always choose the proper CRS for your location and the data analysis that you're doing. As far as what actually happens to the values, uh, this is one of the hardest conceptual hurdles for students. They know resampling changes the raster, but they can't picture what's actually happened to the values. The raster values feel abstract, especially like for continuous data. And when they hear like bilinear or cubic convolution, they imagine complicated math, but they don't sort of visualize what's actually going on. They don't realize that resampling is essentially just reaveraging or reassigning values. That's it. We've got a new grid space. It's not the same as the old grid space. We're going to re-average some values from the old one to create the values in the new one, or we're going to reassign values from the old one to certain corresponding ones in the new one. That's all. So when you resample, you think, what values should go in this new cell based on the surrounding old cells? Nearest neighbor just copies from one to the other. Bilinear takes the four nearest, average them by distance. Cubic uses 16, fits a smooth curve to estimate the values. Hopefully this has helped you. If you want to learn more, you're thinking about going back to school, you want to advance in your career, you don't want to quit your job, you don't want to become a student full time, you don't want to move across the country to that school your dream like Western University, then sounds to me like fully online, fully asynchronous distance education might be the route you want to go. And it just so happens we've got that degree program here at WVU in GIS and spatial analysis. We do have virtual information sessions, several in the fall, several in the spring, even do some in the summer. So if you're thinking about doing it, don't wait a day longer before you begin looking into it. Check us out. See if we meet your educational needs, and if not, maybe you'll find someone else that gives you a better program, a concentration in an area that you're more interested in, a better price, a better academic profile, whatever you decide is important. We certainly hope that we fit the bill in terms of what you're looking for, but if not, we'll do our best and hope that you'll learn from us to help figure out what you really want and find the best fit for you. If not with us, then with someone.